Okay, so we will finish up this discussion of hard drives with a look at disk scheduling. And we'll start with the way things were done a long time ago when the operating system had to handle I/O requests and schedule the disk using a disk scheduler that might be running in the operating system itself. That's the way we used to do things, but with the modern hard drives, it's less and less the case that the kernel knows much about the geometry. So that's what happens with disk scheduling is whether you do it in the operating system kernel or on the device itself, you have to deal with the geometry. And so you have to be careful about how I/O requests to different locations on a hard drive is managed because of potential delays. You don't want to wait for a whole rotation, or you don't want to access the innermost sector followed by the outermost sector because they're quote unquote far away from each other. So you want to do this in a way that'll make delays as small as possible. So it's the job of the disk scheduler to examine these requests and decide which order these requests are going to be satisfied. And so you might want to choose the order of I/O requests that'll give you the slowest, or not the slowest, but the smallest possible delay. Make it as fast as possible. So by estimating the seek time, the rotational delay, and the transfer times, and we just saw in that previous example, the transfer times may be actually pretty small if you're just accessing a single sector at a time. But of course, if you have hundreds of sectors, that transfer time will be roughly on the same order of magnitude then as the seek times and the rotation times. And so by estimating these things, the disk scheduler can use a good approach, and a good one is the shortest job first principle. Get the shortest jobs done first. And so that will give us this SSTF, or the shortest seek time first. If you just sort the I/O requests by tracks, so go in the order of tracks. And so for example, if you're at any track at a given time, pick the request for the nearest track. So if the read-write head is at sector 30, which is right here on the innermost track, and we have requests for both sector 2, which is on the outermost track, and for sector 21, definitely we should pick 21. Chances are by the time you move the head to this next track over, it's just 2 sectors away, but probably the time needed to move the head is probably about the same as the rotation that it takes. It might be off, but let's say it is. Let's say the time needed to move the head is about how much it takes for the 21 to move right over the head. Then we are going to be exactly ready for that sector. Whereas if it was 2, you have to if you do the 2 first, even though it did come first, you might have to move the head 2 tracks down and then wait for this all to rotate all the way over here. So we can do things out of order, even though we are asked to read 2 and 21, let's say, or write, it doesn't matter. We can reorder these requests so that we do the 21 first and then the 2. That can happen. It used to happen at the kernel level. Kernel used to know about the disk storage pattern geometry and would make these decisions in the kernel itself. But of course, in more recent hard drives, you don't do that in the kernel because that's it's just kind of messy. If you had a hard drive with a particular geometry and then you swapped it out, and then you have to essentially know the geometry of that new hard drive. And so usually these things are handled in the device driver. Okay, so bottom line is that if you minimize the seek time, then the way to do that is just sort the I/O requests by tracks. Pick the nearest track first. So older operating systems had drive geometry information in the kernel itself, but as we said before, newer operating systems tend to be device agnostic. There's just no need to know all of those complicated structures, actual geometries in the kernel. So the actual geometry might look like this. You have, in this case, 3 sectors. Of course, you have thousands of sectors in a real drive, and you have thousands of tracks, and this only has 3, and then there's just about 36 sectors total in this case, but in a real hard drive, it's once again thousands of sectors. And so this might be the actual geometry, but the operating system views it as n sectors from 0 to n minus 1, and it's just one long linear array. And we know that's not the case, but that's good enough. The reason for this is the drive geometry is not always available to the operating system. And so the operating system can approximate this SSTF, shortest seek time first. Shortest seek time first using sector or block number. So you can go to the nearest block first. And that might actually work out if you use track skewing, those kinds of things that we talked about earlier. This nearest block first might be pretty close to getting the closest track. Okay. So the nearest sector is always chosen, then distant sectors unfortunately may never get a chance to be accessed, and so this might result in starvation of the sectors that are far away. Of course, we don't want that. That's not a good situation where sectors that are far away we never get there, because we always have something closer to attend to. So we don't want this to happen, and so we want to avoid starvation but implement something like SSTF. How do you do this? It turns out there's a whole bunch of methods that people have used in the past and that are used today too. These are called scan algorithms. That is, the head moves, or the arm moves across, scans the whole all of the tracks from one side to the other, and so they're called scan algorithms. So what you do is move the head back and forth across the tracks along the radial direction while there are I/O requests. Otherwise, you just keep the head stationary. You don't need to move the head if you're not getting any requests. Requests are then serviced only in the current direction of the arm movement. So you decide which way you're moving, and then you find the requests to handle and that are next up in the direction that you're moving. So when the head reaches the edge track, either the inner edge or the outer edge, arm just reverses direction, and then you can handle things that you missed. A sweep in this case, that is when you sweep the head back and forth, is a single pass from one edge to the other, from the inner edge to the outer, or from the outer to the inner. And then a request for a sector on a track that was just serviced will be put on the queue for the next sweep in the other direction. So if you just finished accessing a track and you're moving on to the next track, whether it's inner or outer, and you get another request for the track you just got done with, you'll have to wait till the head isn't going, reaches the one end and then heads back in the other direction, and in that sweep that's when you get around to satisfying this request. So that could be a big delay. So there's a couple of algorithms. fscan uses 2 queues of read-write requests. It doesn't matter whether it's read or write. During one sweep, all the requests in one queue are serviced, and incoming requests, while it's going through that sweep, are put into the second queue. So there's 2 queues, one for each direction that you're moving in. At the end of the sweep, let's say it's going from the outer to inner, you reach the innermost track, the head will reverse direction and head back to the outermost track, and during that sweep the second queue is locked and you're not going to make any changes, and then you service that second queue, and any new requests that come while you're taking things out of the second queue will go into the first queue. So you can think, let's say you're moving from the outer to inner, that's the first queue. The inner to outer direction, when you head in that direction, it'll be the second queue, and then you go back to the first queue for the outer to inner, and so on, back and forth. So requests for nearby sectors are ignored, and so there's a little bit of delay. That's not so bad compared to starvation. So there's no starvation. You just have maybe like a worst case scenario where you're going from outer to inner, and just let's say right in the middle you pass one track, and then you get a request for that track itself. You have to wait till the head goes all the way to one end and comes back, and then you catch that request on the rebound. Okay, there's also circular scan algorithm, and that uses one sweep direction, outer to inner only. After a single sweep, the head goes as quickly as possible back to the outer track, and then you do a slower maybe sweep direction from the outer to inner. So why do this? Mainly because in the case of the F scan, where you go two queues and you go one direction and then you service in the other direction, the middle tracks are serviced twice, it turns out, in one sweep, while the outer and inner tracks have to wait for two sweep times. And so in the worst case, the innermost tracks and the outermost tracks have to wait, whereas the middle tracks, you get everything done much faster than the outer or inner tracks. So a little bit of unfairness in the F scan that you can remedy with the circular scan, and so this is considered fairer to the inner and outer tracks. But of course the middle tracks now have are a little bit worse off, but then on the whole you'll be fairer to everybody using a C-scan, circular scan. Okay, so the crux of the problem is, how can the operating system account for the disk rotation costs now? We've handled sort of the seek time delays, but these scan algorithms do not account for the rotational delays, which we talked about first. So for example, if the head is at sector 30 and you get requests for 16, which is over here, and which is on the next track, but you have to rotate quite a bit. So 16 once again is over here. The head is over here. If you move one track over, you will have to wait for almost an entire rotation before you can read 16. And the alternative is to maybe service a request for sector 8, which is right here, and there's a good chance if you move this head over to the outermost track, you'll get there just in time to read sector 8. So which one should you do first? Of course you want to do 8 first, because that's going to be faster. You could probably start moving this to the outer track, read 8, and then once 8 is done, you can move it back to the middle track and you'll have plenty of time to read 16. Okay, hope you can see that. So how can we implement an algorithm that's more closely approximates this shortest job first? Because in this case, sort of the shortest job is this first and then 16. So you have to take into account both the seek time, that is the time needed to move the arm from here to here, and also the fact that these platters are rotating at a fixed speed, and so things that are sort of closer in rotation should be done first rather than these things which are farther away as far as rotational delays. Okay, so in that situation we use something called shortest positioning time first, SPTF scheduling. So if the seek time is much greater, and that's what this greater means, is not just greater but much greater, than the rotational delay, then in that case the old approach SSTF is good. However, ideally you want to always choose the request with the smallest total seek time plus rotation delay. And so as a result, if your seek time is less than the rotation, you would say that SPTF, shortest positioning time first, would be better. So this makes total sense when you look at the geometry, but the problem is these days the operating system does not have this disk geometry data. And so as a result, shortest positioning time first, where you account for both seek time and rotational delay, is probably best performed on the device that's controlling the hard drive itself. And that's the direction pretty much all drives are taking, is that these kinds of scheduling is done on the disk itself. The disk has enough memory to handle these requests, and it can line up the requests in such a way that it'll minimize the overall I/O time. So older operating systems did all the disk scheduling, but these days things like SPTF is probably best performed by the drive itself, by the drive controller. And so modern disks actually do a lot of scheduling themselves. The operating system just picks a good set of requests and asks the disk to schedule them, and the disk can use any scheduling algorithm, but if it has enough information about the geometry, it can go ahead and use this shortest positioning time first algorithm for scheduling. One last thing that we want to look at is as far as on-disk scheduling is I/O merges. So what if you get a request for sectors 33, 8, and 34? So here you are at position, your head is positioned right over sector 30, and you want to read 33, which is over here, and 8, and then 34. In such a situation, you don't want to read 33 and then zoom all the way to 8 and then zoom back, because you'll miss 34. You probably want to do 33 and 34 together. So you can handle requests out of order. That's fine. And you want to optimize the total amount of I/O time. And it turns out disk schedulers on the drive will know something about the geometry and will realize that sure, I have to read 33, 8, and 34, but 33 and 34 are right next to each other. I can read that basically in one go, and then once I'm done with 34, I can just move this over, and by that time, well, it'll be a little bit of delay to get to 8 because it has to go all the way around. But the bottom line is disk schedulers can do this I/O merging. You're merging 30 requests for 33 and 34 into one request. And that's faster than breaking it up into 3 different requests and going from 33 to 8 to 34. Alright, so those are some of the main ideas for disk scheduling, and these days what you're much more likely to see is on-disk scheduling, because these controllers know the geometry, and that's usually the best way to handle disk I/O scheduling. Okay.